Large, complex, mysterious. 3 words that aptly describe the human brain. No other organ poses so many riddles in research. Medicatradefair.com is visiting the annual meeting of the German Society of Neurology in Düsseldorf. Here, we talk to experts about neurology in the 21st century, its possibilities and its limitations. Professor Gold, why is brain research so difficult?
We're
not able to simply open up the brain and take a look inside. We are also not able to randomly place electrodes. We virtually have to measure functions from the outside without injuring the brain. The second reason is that the 100 billion neurons are connected to thousands of other nerve cells. The dynamics of these connections make improbable demands on data processing. What can we expect from neuroscience in the 21st century? I think based on today's demographic trends and the aging population, the challenges for neuroscience will keep increasing for us to either protect our brain from aging or making natural replacement functions available as we age and our brain functions diminish. Where will neurology reach its limits, in your opinion? We reach its limits when we try to re-establish entire brain regions in their complexity. There are stem cells that generally have the capacity to repair, but we will face limitations in finding the exact right connections to restore or maintain a personality. Brain-computer interfaces and implantable electrodes have been researched for many years. Can these types of technologies revolutionize the treatment of neurological disorders? Things are already happening in the area of implantable electrodes, and we've already seen some sensational successes in Parkinson's disease, but also some problems. I won't keep that a secret. The brain-computer interfaces could enable an organic transition between brain functions and missing so-called effector mechanisms. We're now talking with Professor Christian Elger about an actual therapeutic application of implantable electrodes for patients with epileptic seizures. Professor Elger, what happens in the brain during an epileptic seizure? We're not exactly sure what happens. We suspect there's an imbalance between inhibitory and excitatory neuron activity. This results in rhythmic discharges of individual neurons that activate other cells until morbid external phenomena appear such as convulsions, cramps or abnormal behavior. Epilepsy can be treated with various surgical measures. One of them is the implantation of stimulating electrodes. What exactly happens in this case? The most researched procedure is deep brain stimulation of the thalamic nuclei. Electrodes are implanted into the 2 anterior nuclei of the thalamus. These electrodes stimulate this region at regular intervals. Due to the connection of this region with the so-called limbic system, we presume to have a positive impact on the seizures that take place in this area and that are very frequently pharmacoresistant, meaning that they cannot be treated with drugs. What results do you see after implantation? Initially, the implantation results in a temporary improvement in many patients thanks to the surgical intervention. The stimulator is switched on later for a percentage of patients, and this is when we see the effects. We assume that the seizures are improved by 50% in 30 to 40% of patients. We already spoke with Professor Gold about the prospects of neuroscience in the 21st century. What trends do you see in your area of expertise? Our specific field aims to improve a small group of patients. So far, this small group can verifiably not really be helped with drugs. The drugs garner only small improvements. That's why the future focus will probably be on surgical or stimulation procedures, and we need to understand more in this area. One of the most important examination methods is modern magnetic resonance imaging. It's making continuous progress. We're beginning to understand the networks of the brain and are thus able to specifically intervene and hopefully improve the patient's condition. Epilepsy is a disorder of the brain that we know comparatively well. So far, we're only able to treat the symptoms of other diseases such as Alzheimer's disease, Parkinson's disease or MS. We still don't know enough about their origins, and this makes it difficult to develop effective therapies. That's why we can look forward to seeing what other things neurology will discover in the 21st century.